Hi everyone. Today we are going to be talking about what every HPC user needs to know about MPI point-to-point operations such as MPI Send and MPI Receive. I'll give you the basic mechanics of how these operations work and how you can use the Survey HPC performance tool to determine how these calls are consuming the resources of your HPC system. If you are interested in a more general introduction to MPI, please check out our Beginner's Guide to MPI Testing video. There's a link to it in the description below. Survey is an HPC performance tool from all of us at Trenza Synergy. In an MPI application, it is very common for two different ranks to exchange information with each other. This is known as point-to-point communication. The most basic point-to-point functions are MPI Send and MPI Receive. These are known as blocking calls because while the thread is processing one of these calls, it has to wait until the call is completed before doing other useful work in the application. Here's how it works. Let's say that rank 0 and rank 1 want to exchange data with each other. MPI Send is called on one of the ranks, say rank 0. The data is copied into rank 0's internal send buffer. At this point, the data is safely ensconced away so that the function can return control to the application and allow it to continue its work. Internally, though, the data is pushed out over the network on its path to its destination. MPI Receive is meanwhile called on rank 1. It waits for the network to put the data into rank 1's receive buffer, which obviously can't happen until the data has arrived from rank 0. After the transfer is complete and the data from rank 0 is copied into rank 1's receive buffer, the MPI receive call is completed and rank 1 can use the new data to do useful work. In many cases, the roles of rank 0 and rank 1 will then be reversed, and rank 1 will send data to rank 0 using the same method. There's another function available called MPI Send Receive. It works the same way as I just described, but rank 0 sends its data to rank 1 at the same time as rank 1 sends its data to rank 0. This, of course, is faster than sending the messages one at a time. It's also possible to use non-blocking calls to exchange data between ranks. In a non-blocking call, the rank can start the call and then go do other work while the call is being completed. In the non-blocking MPI Send call, after starting the send operation, the rank can immediately go do other work. Meanwhile, the data being sent is copied into the internal send buffer and pushed to the network. While this is happening, the sending process is free to do other work. In order to determine when another message can be sent, there must be a call to MPI wait, which blocks until the send buffer is ready again, or a call to MPI test, which reports whether the buffer is available and returns immediately. In the non-blocking MPI Receive call, after starting the operation, the rank can immediately go do other work. Meanwhile, the receive buffer is preparing for the incoming data. In order to determine if the data has been received, a call to MPI wait or MPI test must be made. As before, MPI wait blocks until the operation is complete and the data is fully available, and MPI test returns immediately but reports whether the receive operation is complete. The non-blocking MPI Receive is typically more useful than the MPI Send because the blocking MPI Receive call has to wait for the send operation in one of the other ranks to complete before it can start receiving its data, whereas the blocking MPI Send function just has to wait for its own data to clear the send buffer. For that reason, some applications will pair an MPI Send command with an MPI Receive command. There is no equivalent non-blocking call for MPI Send Receive. Now let's see how Survey measures the performance of point-to-point operations. We are using the Pennant benchmark here. All the runs of Pennant we are going to talk about today were run across 8 nodes, with the number of ranks per node adjusting as the number of ranks increases, so a run of 8 ranks was performed with 1 rank per node. On each node there are 72 cores. Now let's look at the extended MPI metrics with 8 ranks. One interesting thing to note here is that unlike some benchmarks, the Pennant benchmark MPI calls are not completely symmetrical. Here are some of the results for MPI Send. Each rank has an average of 64,600 calls to MPI Send. These calls are all extremely quick, and all added up consume only a small fraction of a second. Here are the results for MPI Receive. There are a similar number of calls to MPI Send, except for the 256 bytes bin, which is empty. And you can see the results for the MPI blocking MPI receive here. Since there are calls in only one bin, we only show those results instead of the entire histogram. When the application has the same number of MPI send and MPI receive calls, then we show the two sets of calls together to make it easier to read. But in this case, not all the ranks behave exactly the same, so the average number of calls for each function is not the same. The results for MPI send are different from the results for MPI receive, so we show them separately. Just a quick note, if you add up all the blocking and non-blocking send calls across all ranks of the application, they will exactly match the number of blocking and non-blocking receive calls. Now let's take a look at a quick summary of the performance results of this run. The total runtime is just over 30 seconds. The MPI functionality only takes up 8% of the total runtime, and the average memory usage of a thread is only 0.03% of what is estimated to be available for that rank. To estimate how much memory is available for each rank, we figure out how much memory is available for use on the node and divide that amount by the number of ranks on the node. In this case, we only have one rank for each node, so each rank has access to almost the entire resources of the node. Now let's take a look at the same application run on the same cluster, but this time with 16 ranks. First, let's look at the number of calls to our point-to-point functions and compare them with our results with 8 ranks. The number of MPI send calls went up from just under 65,000 to a little fewer than 82,000 calls. We know the number of MPI receive calls is roughly the same, so although the number of ranks doubled, the number of point-to-point calls did not. This behavior, where the number of messages increases when the number of ranks increases, is quite common. In other circumstances, it might go up even more or stay the same, or it might even decrease. It depends on the application being used, the size of the problem being solved, the number of ranks, and potentially many other factors. Now let's look at a summary of the performance results. The total time for the 16 rank run is 15.87 seconds. The total time for the 8 rank run was just over 30 seconds. This is evidence of strong scaling behavior. That is, the total amount of data that the job is processing is the same, but we are adding twice as many ranks. For this application, this is cutting the runtime in half. Some applications scale up automatically as you increase the number of ranks. In that case, you may even see the runtime go up as you increase the number of ranks. The MPI percentage did go up a little bit from 8% of total runtime with 8 ranks to 12% of total runtime with 16 ranks. More time is being spent passing data from rank to rank instead of performing computations. The memory usage between the two runs was pretty similar. The average maximum memory usage for a thread in the 16 rank run was actually slightly less than the average maximum memory usage for a thread in the 8 rank run. However, since there were twice as many ranks in the 16 rank run than there were in the 8 rank run, each node had 2 ranks instead of 1. Since all the ranks running on the node share its memory resources, then the 2 ranks will compete with each other for the memory resources. Survey estimates the available memory by taking the total memory available on the node just before the run and dividing it by the number of ranks. So while in the 8 rank run, each rank had an estimated 194.4 gigabytes of memory available to it, in the 16 rank run, each rank had an estimate of 97.2 gigabytes of memory available to it, which is about half the amount. This is only a rough estimate based on the available memory before the run started and the number of ranks on the node. It is not an actual measurement of the memory available to the rank at the time the application is running. When we double the number of ranks to 32, here are the results. The total number of calls to MPI send for each average rank only went up from about 82,000 to around 90,000, even though we doubled the number of ranks. The run total time is halved again, going down from 16 seconds to 9 seconds. The MPI percentage of total runtime went up to 16% of the total runtime. That said, the total MPI time stayed pretty much the same, but since the overall runtime went down significantly, that increased the MPI percentage of the total runtime. The average memory usage per rank is about the same as the 8 and 16 rank runs, but because there were twice as many ranks running on each node, the total memory estimated available for each rank is down to 48.6 gigabytes. Our benchmark is still only an insignificant amount of that memory, but you can see how this could start to be a problem for larger applications. Here are the results for 64, 128, and 256 ranks. If you wanted to optimize for the best runtime given the resources available, it looks like you would choose 64 ranks. The run with 128 ranks has about the same performance even though it used twice as many cores. And the run times with 256 ranks actually increased, which is common behavior for MPI applications. Adding more ranks does not always increase performance, as the number of time spent passing messages increases as a percentage of the total time for the run. In summary, when you increase the number of ranks in an MPI application, the number of point-to-point calls will increase, but they will not necessarily increase at the same rate as the number of ranks is increased. Doubling the ranks does not double the number of point-to-point MPI calls. Second, while the total amount of MPI time in our example did not significantly increase as we increased the total number of ranks, the percentage of time performing MPI operations of the total runtime of the application increased as our total runtime decreased. Third, as we increased the number of ranks, each rank still used about the same amount of memory. In other larger applications, however, changing the number of ranks may significantly change the amount of memory used in each rank. In any case, as we added ranks to the node, the estimated memory available to each rank decreased, since these ranks share the node's memory. And that's the end of our presentation on MPI point-to-point operations. If you enjoyed this video, please give us a thumbs up. If you would like to see more presentations like this, please subscribe to our channel and turn on your notifications. If you have a suggestion for future videos, please let us know in the comments below. Thanks so much.